Welcome back to our virtual symposium. And in this second part of the symposium, actually, we will have three more talks, not two, like I said previously. So we have three more talks, starting with the talk of Scott Makeig, our second special guest here in our event, and as we all know, a pioneer in the field of mobile brain and body imaging, among other things. So if Scott is ready, I would like to make him a presenter, and I look forward to his talk.
Very good. Now, are you seeing, let's see, show my screen, is that working?
Yes, we see.
All right. So let me move this here and begin. So I thank you for the invitation. I thank the Brain Products, and certainly for its sponsoring the MoBI Awards. It's a very, very good thing, I think, to bring some attention to this fledgling but growing field, and of course to Klaus and to all my other collaborators who've helped pioneer this direction. Now, I need to advance my screens. Good. All right, so this was the original slide I made to talk to the U.S. Navy Basic Research Unit to try to get funding for a MoBI lab. And I said, you know, that it's true that wonderful progress is made in brain imaging, but in all those modalities, even in EEG, much of the time there was a fixation cross, and in all of them, you were told to keep your head extremely still because the fear of motion artifacts, which were thought to be intractable, and in most for MEG, fMRI, PET, and so on, the sensors were very heavy. You had to hold your head against them, and you were told not to move, only move very minimally your fingers or something. So why was this? Well, as I said, there were limitations both in the analysis and in the sensors. But of course, and this is the slide I showed, not something we went to immediately, modern dance, but the idea of natural cognition as being predominantly to control our behavior, or more explicitly, the results of our behavior. And so, since our brains have evolved primarily to do that through evolution and into human form, we certainly can be suspicious that we haven't been able to see the full repertoire of brain dynamics that support our experience and our actions by having people staring at a screen or lying prone in a scanner. Okay, so I thought it was so important, such an important concept, and that an acronym was worth attempting. And fMRI had its 4-letter acronym, so I thought, well, MoBI we should say that what we're doing is recording both the brain and the body, that is brain and behavior, but a larger bandwidth of behavior. In fact, what we want to do is record what the brain does via EEG and other imaging modalities, what the brain experiences through records of the experimental conditions, and including scene cameras, world recording, ultimately, and what the brain organizes. And of course, what the brain organizes our behavior, which traditionally in psychophysics had been recorded as, you know, a button press once every few seconds, with the button press being considered to be a point process, both in time and space. In other words, having no extent, no duration, and which of course is kind kind of nonsense. So this was the concept, and we were fortunate enough to get a grant so we could begin building a lab and software and so on. So of course, there's many other words that could be used and are being used. Neuroergonomics has been around for quite a while, Saramann's term. Real-world neuroimaging is an attractive term, and I very much like Klaus Gramann's pointing out that what we're trying to do is really image natural cognition. So in these different fields, this urge toward learning, looking at natural cognition is as the technical and instrumental possibilities increase, and the analysis also becomes more flexible. This is a field that is, as I say sometimes, is an interdiscipline, not a discipline. And of course, Klaus already mentioned the very key term, which has come increasingly into psychology in recent decades, I should say, but years, of embodied agency, whereby even our concrete, abstract, or our aesthetic cognition faculties are all built on, grounded in our embodied experience of being a purposive agent in a 3D space-time world with a body, embodied, and not a disembodied brain in a scanner box. And that is our natural cognition. That's how natural cognition evolved through animal forms, and it's what we fully enjoy as humans. So how can one break down what is the types of natural cognition that we should, what are the modes of natural cognition? So I was reading in a book of spiritual discourses, and there was this comment. It was by Avatar Meher Baba, and he happened to mention that humans have full consciousness of the world in all the aspects of knowing, feeling, and willing. And it occurred to me that that is a very, very nice, or can be used to make a very nice sort of topology of ordinary human consciousness. If by knowing you mean all sorts of attention, learning, memory, and perception. And by feeling, of course, you mean those experience, that aspect of experience that has to do with feeling and not direct perception. By willing, all forms of intention, purpose, agency, intended movement, conscious, acting as an agent in the world. Then you have a very nice breakdown where you begin to see that the scientific study of the mind, the scientific study of natural cognition, should really explore the interrelationships between brain processes and systems that have evolved to serve and to balance all these three aspects of cognition. So I would emphasize that brain imaging and EEG and particularly MoBI research methods can be used to learn better how the brain and nervous system support and sustain human consciousness in all these aspects, which together comprise our natural cognition, I would say. Well, we did get the grant, and we were able to build downstairs a MoBI lab, and particularly because we had very good help on software. And particularly on the left there, upper left is Christian Kota, whose wonderful lab streaming layer software is freely available and supported by companies increasingly, including brain products, I'm happy to hear, and is now interconnecting a very large number of devices. It comes with an extensible data format, and Christian also gave us SNAP, a programming framework based on Unity, with which one can design experiments as complicated as real-world multiplayer video games. On the lower left is Alejandro Ojeda, who built the multimodal browser, the MoBI Lab browser that's attached to EEG Lab. And particularly, I'd like to also mention Nima Bigli-Shamlo, who is there in the middle of the screen behind the lettering, who, among other things, for his PhD, invented a system. The first system is still the only system for detailed description of experimental events, the hierarchical event descriptor system, the HEAD system, which increasingly we're working on to make it a fundamental part of imaging, archiving, and therefore meta-analysis and machine learning on EEG data. The HEAD system was recently incorporated formally into BIDS at the top level, so that all the BIDS standards, including EEG, inherit the acknowledgement and endorsement of the HEAD system for describing events. No longer will it be the manufacturer's event number 3 or target or some, you know, some really indecipherable code for what actually happened when the recorded event occurred. Now one can actually use text and text tools to record with as much detail as you can or would like or can stand exactly what happened in your experiment. Why? Because those who will analyze the data after your first analysis, and when it becomes contributed to a national or international data archive and becomes part of hopefully of large-scale analyses that derive the benefits of all the artificial intelligence and machine learning progress that continues to be made. When your data becomes part of that very large asset, world scientific asset, then the nature of events occurring in these brain imaging data sets of any kind can be compared to each other. So currently the HEAD system is being prepared. It was sort of it was kept alive by an Army project by Nima and Kay Robbins, and now we're bringing it back under the SCCN GitHub site, and we're working on HEAD version 3 to make it compact, extensible, and we'll have an opportunity to actually apply for support for that process. I hope that it becomes ready for prime time, ready for proselytizing, educating, and increasing use in the near future, including in our own database, the NEMAR database. That's NEMAR, no Y, and under the Open Neuro Initiative in the United States, which will house and is already to some extent houses EEG data sets for analysis, meta-analysis, but tied into a framework of access to US supercomputing sources. And that's not just for US researchers. For almost any nonprofit institution, researchers in the world can get a count on the US Exceed network. It's tied directly to EEG Lab now. You can ask for your script to be run on the supercomputers. instead of on your local computer, directly through the EEG Lab menu. And the data that is in the NAMAR database, the OpenNeuro/NAMAR database, will be directly available for large-scale analysis on the Exceed network via the Neuroscience Gateway. Okay, so some MoBI studies. I would say in the 10 or more now years that since we began that, since Klaus joined us, Dan Ferris was with us at that time, and we excitedly charted out the prospect of MoBI research. I have to say I've been disappointed in one thing, and that is we haven't found any collaborators from the biomechanics world. Physics trained people who would like to make open source kinematic software at least, and then open source biomechanics software that ties and have an interest in tying that very technical but well-developed world in with the world of brain imaging. So those type of technical collaborations I very much still look forward to, and I think it behooves us all to try to bring about. Again, this field is too large for any one of us to master everything, or certainly to have mastered everything in the past. So collaborations are the result, are the essential. And one such collaborator here is Hiroyuki Kambara, who was with us for a year or so. We went hiking in the Sierras, and I gave him the idea of doing juggling. And sure enough, there's Johanna Wagner, postdoc now with us, juggling lit balls. There's a camera to the right that's recording everything. And there is some EMG sleeve on her arm and high density EEG. Juggling, of course, is as old as the Egyptians, as we see on the lower left there. And his results to date are really impressive. These are all now time locked to the juggling cycle. These are time frequency pictures, so these are what we call ERSPs, spectral perturbations. So this is frequency here, and then this is time, but it's in terms of cycles. And these are independent component processes from I think multiple subjects, because here's a cluster. So what you see alpha rhythm that clear and significant alpha rhythm changes within the cycle, within the cycle of throws, and one hand throws, two hand cycles. We see an alternation of different frequencies. We see gamma bursts. This is 50 to 128 hertz, I think. We see time to particular. So this is a little bit right-sided. So this may be the left hand throw, for instance. I don't have the details. In very particular was this discovery, which turned out to be a rediscovery of extremely narrow band, high frequency, 75 hertz bursts. I think if we actually sonicize this, or oralized it, what do you call it? You could actually hear a tone here, being. But this was on one of the hand throws, and this was a right motor source. And you see here's two frequencies that show up for this IC, and so on and so forth again. This was just extraordinary to me, because I've never seen anything that high, a narrow band that's not endogenous into the brain. But it turned out that a neurosurgeon working with ECOG and some simple motor tasks in San Francisco had seen it already at the cortical level, and so we confirmed it at the scalp level. And of course, we can explore in the whole world of MoBI when this occurs and when it doesn't. So this was a movie. I think it'll go slowly here on the screen, but where he synchronized the causal information flow on the left between sources in independent component sources in Johanna's brain as she juggled, and everything was time warped so that it was time locked to the average swing cycle or the juggling cycle. And this is just the beginning of even the analysis of these data. We're now working on an algorithm with Wes Thompson to do very sophisticated clustering of such movies across subjects using hierarchical Bayesian learning models. So there's a world of research in how the visual system, the motor system work together in a complex motor task. Now, what about the feeling system? So that was had to do with the willing system, and of course the knowing system, knowing where the balls are, and the willing system of actually willing them to stay in the air. What about the feeling system? So we've done a series of experiments over the years in that, and this was Julie Anton. She and I did an emotion imagination experiment where we very carefully had subjects sit quietly and imagine different emotions, in fact, 15 different emotions. And then we looked at the state of the brain dynamics in those different emotions and looked for distinguishing features of the brain state. And this was actually just high frequency activity in a rather elaborate analysis. But the analysis was done without any knowledge of what the different emotions were. And you see, if you project all these down to this valence line here, these map the position on this line maps almost precisely to the ratings of positivity or negativity. In other words, the valence of these sorts of emotions. So we ask another whole group of subjects to rate whether, how positive is love, how positive is awe or contentment, and so on. And the correlation of their values with the brain, with the data-driven brain ratings in this space had a correlation of 0.96. So yes, there were motion is registered in the brain. Here we use the high frequencies, but there was lots of information in different frequency bands. It was very hard to publish even that because the analysis was rather elaborate, and but we finally did. And what we found in particular was that the most consistent areas that in which this high frequency, the size of this high frequency activity showed how good you were feeling, basically, or bad, were these two areas here. We looked in the EEG and fMRI, well, the fMRI and the PET literature at that time was not very good. We didn't. But then, since then, here we flipped it around for the neurological convention. And since then, we found several studies in which the same areas have been found. And so the brain and EEG exhibits all sorts of, contained in it, there's all sorts of information about the feeling, the world of feeling, consciousness or cognition. And so Grace Leslie arrived from the music department and wanted to study, are we really engaged in the music and listening to the music? And so there was this, I don't know if this will play, this was a classic American movie where she was trying to tell her deaf friend how to listen to the music. And he said, well, I hear something. And no, she said, she started going like this. Well, we had that same idea and we took it into the lab. And so the subject there was watching the moving dot. The moving dot was slave to the position of his hand. And he was beating time like a conductor while he heard dramatic movie music. And I don't know whether this will play. I guess the sound isn't on, but he's listening to some, you know, film music, and he's trying to, this is not a musician. He's trying to convey to his imagined friend the feeling of the music, even though his friend is deaf and can't hear anything. So he's trying to convey with these movements, not just what the timing of the music is, we made that quite clear, but the feeling of it. And then we looked at the brain activity. Well, first of all, we showed a lot of people online these animations. Here's the person was, well, in which of these was the person more engaged? And in which of these was the person more rote, because they also had a mental arithmetic task with working memory to do at the same time? Well, it turns out the World Survey Monkey audience figured that out. There was about 75% correct. So the information in those sweeps is there, whether about the emotional engagement of the subjects. So what happened in the EEG? So with the ICA, we can find many sources. These are clusters of sources across quite a few subjects. Of all the data that we looked at, time locked to these swings, these intentional communication of emotion, we found one difference between those two task conditions, and that turned out to be the right temporal parietal occipital junction area, in which there was more theta bursts at the beginning of the cycle, and not that was, and at the end of the right hand swing cycle, there was another theta burst that was emphasized in the fully engaged emotional condition. Well, if you look in the fMRI literature for the right temporal parietal junction, you see lots of things, including hand motor control and emotional control. And it predicts the volume of tissue there predicts the level of emotional awareness of others. So what we were seeing there was not the theory of mind of the subject, but the theory of heart, you could say, or the feeling of heart. In other words, they were actively trying to express to another person using hand and arm movements. And for that, the right temporal parietal junction, the fMRI papers say, is a key and unique structure. So again, we found it with source result EEG. Okay, so enough of that. What do we need to do? Well, hardware advances are ongoing and welcome and will continue, I think. I've talked about interdisciplinary collaborations, and particularly with physics-trained biomechanics research community that has studied very carefully movement representation. How do you go from a simple motion capture system recordings to understand what the actual movements of the individual person's limbs were, and what forces were involved in creating those movements, or even all the way to which muscles were doing what. There is no open source kinematics framework we've discovered so far. There should be. The problem of scalp sensor and brain or brain imaging co-registration is a key one. We're working on that with portable photogrammetry. And then motion capture sensors and body co-registration system. Again, even if you have a nice motion capture system, either wearable or room-based, how do these all fit together to create an accurate open source kinematics framework? And then what about a brain-centric movement coordinate system? And this, I think, exists, as well as creating a event descriptor system for movement events. button press. That's good because it's a very simple motion. But well, all the way to choreography, dancers have systems for recording their movements. And then combining that, of course, with high resolution EEG source imaging, which is also advancing. So this was our, in our manifesto paper, this was an artist's conception of a MoBI suit of some sort. Well, here is a breadbox solution by a very talented just Ph.D. from our lab, Siddharth. And this is an AR system where he's using eye tracking. No, in this system, he doesn't yet have the glasses where you can actually add information. He has ECG, everything's very portable, extremely portable. He has EEG, dry electrode system, and so on. And of course, he's finding that big companies are very interested in all this, names of whom, which you know, because you use them every day on the computer. So this will continue to advance. There's also now a IMU inertial motion unit system that has no wires, that each little device is just attached like a Band-Aid and operates through radio signals. So there's a wonderful world of microelectronics that's ever advancing that will make MoBI recordings more and more natural. Here is this natural basis for human motion that I very much like. Hiro Tanaka has worked with us, but somehow he's an example of a physicist, not a biomechanics person really, but who realized that there was a more natural system for representing movements than the XY position of your elbow and your wrist, or the robotics system of joint angles and torques. When we reach for something, we're really not aware of what our joint angle is unless it, goes straight. And but we are very aware of how far our wrist is from our face, from our body, from our chest. So he built another system, a technical mathematical system for representing movements, body positions, and then movements in terms of all these distances, which he argued is much more natural for the brain to operate in terms of, and turns out has mathematical advantages in terms of making the equations of movement not just a page, but a very short, compact representation. So far, this has not been put into kinematic software. It has not been, there's no translation of mocap information into this coordinate system, but I look forward to it because when that happens, I'm quite sure that we'll find a much more natural match to EEG phenomena during experiments recordings that involve natural movements. Finally, why not go on and image, use all these techniques to image social interactions and aesthetic communication? Well, we saw something about aesthetic communication in the conducting experiment. But this is a picture from a actual therapy session. And what about all the faculty, the feeling faculties that allow us to have appreciation for the depth of feeling of these people and for what this feeling seems to be? It's so difficult to pull out feeling information from each other, partly because we hide it. And we're not even aware of what our perceptual system uses to judge feelings even in this extreme picture, where there's a whole poignant story there in front of our eyes that we can appreciate, at least in feeling, without being aware of what it is where is actually cueing us to that. So the sort of with the objective vision system and attention and focus and so on, is quite different than this feeling perception system. So yes, it would be very good to image that. And I will skip this and this. And just to say that one can do experiments with even kids. This was Gideon Diak working with us, kids and moms, popping bubbles, and doing source resolved brain imaging. And so I don't think this is, this is really the beginning of a very exciting era for brain imaging, and particularly for mobile brain-body imaging, in which there's all sorts of possibilities of brain-machine interfaces, functional, electrical and electromagnetic imaging, MoBI, and so on. So it's a very exciting time to get into the field, although one has to be prepared to enter into the collaborations and become familiar with the technical fields that have to come together to really make progress. So, thank you.
Thank you very much, Scott. Thank you.